Thank you for the invitation. I'm really happy to be again back in Vienna. So actually, I was here at the ESI as a junior research fellow in 2021, so in the middle of the pandemic. And unfortunately, because of that, I lack a bit of the magic of the place because there was nobody to talk with. So luckily, this is not the case. And then also, it was nice that some of you were also present at this little hybrid workshop that I organized with Barbara. And I do remember that in that case, there was some chat between you and Tomasz to organize a later bigger event on this infinite dimensional geometry. So I'm happy that this finally managed to take place in these occasions. Okay, so as you can read, I will talk about a work which I did with Alfonso Garmendia. We put it on the archive last summer, so you can have a look there if you want more information. And this is about PB-groupoid versus VB-groupoid. So before focusing on actually the word groupoids, let's just remove it and just does PB and VB. So this means principal bundles and vector bundles. That's where I want to start for having just step number 0 of what we are interested to do or where did we start with. I want to recall the standard correspondence differential geometry between vector bundle and principal bundles. We know that if we start with any vector bundle of a certain rank, then one can construct the so-called frame bundle. This frame bundle is just, as a set, is just the collection of all the possible frame of a vector bundle, meaning all this linear isomorphism between the fiber and Rk. And if we put them all together, not only does it define a set or a space, but this is actually a manifold with a nice projection on M, and it has the structure of a principal bundle with group GLK, so the invertible matrices of dimension k by k. On the other hand, one can also start with an abstract principal bundle with the Lie group G. We need to fix an additional data, which is a representation V. And then in that case, the converse construction is what is called the associated bundle. So one considers simply this product P times V, and then quotient by the diagonal action of G. So where G acts on P by the principal action and on V being a representation. This construction yields also a nice bundle, which is a vector bundle, which has as rank precisely the dimension of this representation. So in particular, if I take a start here on the right, again with a principal bundle where G is GLK, I can take as V simply Rk, and then I get this correspondence. So this, as a corollary, one has this correspondence between vector bundle of rank A and principal bundle with structure group GLK. And this standard result differential geometry can be very useful because it has been used to transform notions and problems from one side to the other side. So for example, I can mention that one can look at connection from the point of view of vector bundles, so linear connection, and on the other hand, one can transform it into connection a principal bundle in the sense of connection one form. Or something else that also that I'm quite interested in, that for me was one of the motivations to start, is that one can look at various kinds of geometric structures which are defined along the fibers of vector bundles, in particular when the vector bundle is just Tm, the tangent bundle of a manifold. Think of something like a Riemannian metric. And then on the other side, one can try to encode this notion, this geometric structure, as a reduction of the structure group of the principal bundle. So in the case of a Riemannian metric, for example, here one would just take the bundle not of all frames, but of the orthonormal frames, which is naturally a OK bundle. And in general, one can do it for many other kinds of geometric structure, for symplectic structures, for foliation, complex structure, and so on. And so there is really the theory of G structures, which is really born out of this idea. So this shows that this correspondence can be quite useful and interesting to study. And the main question that we wanted to address would be, what happens if we try to replace M with a Lie groupoid, G over M? So I will explain then what do I mean exactly by that, why and how we can try to address this question. But first, as Madeleine mentioned, that she introduced what is a Lie algebroid, because I think half of the audience here is very expert on the topic, but the other half probably is not so familiar with, and I assume that the same holds also for Lie groupoids. So I will have the honor to tell to some people that might not have seen what is a Lie groupoid, but I'll do it here very quickly. So I assume that instead people are familiar with Lie groups. Well, a Lie groupoid is something which is very similar to a Lie group. It's just that instead of having a multiplication which is defined everywhere, it is only defined partially. So one has still a smooth manifold G. Here, I should maybe turn on just for a few minutes. One has just a smooth manifold G. And then, if it was a Lie group, I would take just the product G times G, and then define a map here, which satisfies the usual multiplication rule. For a Lie groupoid, I don't have a map defined on this, but only on a subset. I have a subset here, which is actually defined as a fiber product, where here I have S and T. So these are two further maps, which I have to give. They are part of the structure of my Lie groupoid, which determines when two arrows, two elements of the Lie groupoid can be composed, can be multiplied. So that's why it is common to denote Lie groupoid in this way, as G over M, where these two arrows will be precisely the source and the target that I have there. And in this way, then one can just ask the standard definition that one has for Lie group, where the multiplication is a smooth map. Here it happens the same, just I have to ask a few extra questions, extra properties of those maps, so those have to be submersions. And then, exactly like in a Lie group, I have also to ask that there is a unit and that there are inverses. So there is actually an inverse map here going from G to G, and then there is a unit map. And this thing with the unit is the other main difference with Lie groups. In a Lie group, one have only a single unit. So you can think as a Lie group as a Lie groupoid where this M here is actually equal to 0. So this M would be the manifold of unit. In a general Lie groupoid, one have many units, and for each element here, then there is here an arrows which behave as a unit. So if we multiply any other arrow by that one, we stay in the same. So that's more or less what is a Lie groupoid. As I said, if you have never seen, think that for M equals 0, then you just get a Lie group. And another, a non-trivial example that you might have seen could come from algebraic topology, for example. If you've seen what is called the fundamental groupoid, well, that is something which is defined exactly like the fundamental group, just that in the fundamental group, one consider loops, homotopy classes of loops, and of course, two loops can always be composed because they are based at the same point. But if instead of loops, I consider path from here to here, I cannot always compose it with another path here. I need the paths to match with each other. But with that one, then it is exactly the same kind of object. Lie groupoids, they are very useful in many practical situations. They arise in many applications, and there are many natural examples. As I said, we will hear it also, I think, in other talks this week, something about Lie groupoids.
Themselves.
Yeah, sure. We can see them maybe since a vector space is actually an abelian group. That's a bit still a way to see those vector bundles groupoid. Okay. So now, the goal of the talk will be indeed to present you, first of all, with this object in the title, so VB-groupoid and PB-groupoid. Now, the main thing is that VB-groupoid is a well-defined object, which is well studied in the past years. So here we'll just have to recall what is the definition and some few interesting examples and properties. However, PB-groupoids are less studied. So there are in the literature a few notions, so several people actually have tried to make sense of what this should mean, depending on which application they had in mind. So what I will present here will be a new definition, which actually encodes all the previous one in the literature that we could find. And we think that it should be a natural kind of definition to take, because we reach this definition by considering the frames of a VB-groupoid, meaning that we apply the same philosophy that one have used before, as I showed in the correspondence between vector bundle and principal bundle. Principal bundle could be seen as the structure behind the frame bundle of a vector bundle. And PB-groupoid here would arise as the structure behind the frame bundle of a VB-groupoid. And that's why here, in the part number 2, I will have to explain you something about the frame of VB-groupoid. And then I will conclude then with this correspondence and some other open questions that we have. So VB-groupoid, well, these are objects which are already quite old. They are older than me. And they have been introduced by Pradin, and there are many equivalent definitions. So one can define it, for example, in this very compact way, as vector bundle object in the category of Lie groupoid, or Lie groupoid object in the category of vector bundle. So if you know what this term means precisely, one can just unravel it and be precise on what the definition is. But I will just later show you precisely, concretely, what a VB-groupoid is. I want to refer just to as a little motivation for those that never heard it, to show how this VB-groupoid could be helpful. So there's been many instances of application for these objects. Well, the first one was not even an application, but was really one of the main motivations for defining a Lie groupoid, and that comes from Poisson geometry, where people actually were looking at integrating various kinds of Poisson manifolds. In particular, one could look at this fiber-wise linear Poisson structure on vector bundles, And when integrating those structures, one finds out an object which is precisely a nice instance of VB-groupoid. And that was one of the main reasons why VB-groupoid started to be studied. Then even after that, in other areas of geometry, they found some nice application of VB-groupoid. For example, one comes in representation theory, or better in representation up to homotopy of VB-groupoids, of Lie groupoids. VB-groupoids comes useful. Another is in deformation theory, where also people try to deform Lie groupoids, and in order to describe how this deformation is controlled, they needed some kind of VB-groupoid cohomology. Or even in non-commutative geometry, in index theory, VB-groupoid have been recently used as a tool for proving certain blow-up constructions. So this hopefully shows that it is interesting to look at VB-groupoid, and that's why we wanted to extend this correspondence, hoping that there will be other problems, instances, or examples related to VB-groupoid that could be translated in the PB words, and hopefully we'll be able to solve better or get better insight in this point of view. Yes?
Representations?
No, it's two-term representations up to homotopy. So it's like there is representation up to homotopy, which is a single thing, and then a special kind would be the one that's two-term as opposed to n-term. And the idea of representation up to homotopy is that for a groupoid you can define a standard notion of representation, which is the analog of what actually Madeleine was mentioning, the representation on a vector bundle. But then, compared to the standard representation of the groups in the algebra, for example, there is something which is lacking, which is the adjoint representation. So we don't have in general an adjoint representation of a groupoid or an algebroid, or at least we don't have it in that sense. In order to make sense of a joint representation, then the Kreinig and Arias-Abad make sense of the notion of representation up to homotopy. So it's an object which is a bit more general, but there one can define what is an adjoint representation. So these were just, these people were instead, Satz and Mehta were interested into defining better what are these object representation up to homotopy, and in the case when it is two-term, then they can just more easily treat them using VB-groupoids.
So this is one name.
Yeah, exactly.
It's not
one single name.
Two-term representations plus up to homotopy, but this is one name. Two-term representation up to homotopy. Language is not associative.
Exactly, yeah, I should have put some brackets to them. Okay, so now what are VB-groupoid? In practice, they are objects like that. So if you look at this, it's a diagram where I have here on the right G over M, so that's a Lie groupoid. On the left, I have EG over EM, that's also a Lie groupoid. Then on the top here I have a vector bundle, and on the bottom I have another vector bundle. And then I ask that everything is compatible with everything, meaning all the vector bundle maps, the projection, the addition, the zero section, they will be Lie groupoid map, and all the Lie groupoid structure map, so the multiplication, the source, the target, and so on, will be linear maps. Of course, it is redundant to ask all these properties. One can actually just take a subset of those, but those has been studied. One can read precisely which kind of property which are the minimal set that one needs. This is what would be a VB-groupoid. In the next slide, I will show you some examples. I want to mention that there is another important notion which is related to a VB-groupoid, which is that of the core, because it will be useful for us later. And the core is what? So it is a new vector bundle that one defines simply by taking the kernel of this map, of the source, and intersect it with the kernel of this other map, the projection. So this defines a vector bundle over M, which is endowed furthermore with a natural linear map, which I call ρ, which is just the restriction of this T tilde to C. This has the name of core anchor, so if this rings a bell for somebody that knows Lie groupoid and the algebroid, this is not a random name, and in the next example we will see exactly why it is called like that. For the moment, this could be just an object which is defined associated to any VB-groupoid, and it's actually quite an important object because basically the core and the base are the two main building blocks for VB-groupoids. And in particular, I will also use actually this notation. I will say that a VB-groupoid has rank LK, whereby these two are just two natural numbers, and they're just the rank of this vector bundle and the rank of this other vector bundle. Yes?
Is this the same as double Lie groupoid, for which one of groupoid structure is vector bundle?
I guess so. So double Lie groupoid. Yes, I guess you want to just check that. I mean, if one structure is a vector bundle, then this.
So this is a particular double Lie groupoid.
Yes. Yeah. There are many actually double structures and structure of this kind where one has commutative diagram as in the sort of a square, and then one just has to impose different kind of compatibility and get different interesting objects. Okay, So what would be now the first example? Actually, the easiest to understand is this tangent VB-groupoid. So if I start with any G over M, then I can consider the tangent bundle Tg, which is a vector bundle over G, the tangent bundle Tm, which is a vector bundle over M, and then here I don't have really to work much because there is a natural structure of Lie groupoids induced, which is just given by taking the tangent factor. So I just applied differential to all this structure map to the multiplication, and I get a VB group and I get a Lie groupoid structure which satisfy all this compatibility. And then, yes, please.
Is this in some kind a semi-direct product?
So, like in general, like one can actually look at making various kind of semi-direct program, in particular of the core and the base to define to build a new VB groupoid. So
I mean, for a Lie group, that's a semi-direct product of the Lie algebra with the group. So this could be a semi-direct product of the groupoid with its algebroid. Is there anything like that?
No. I think you only have there is, but you have to take more specific or particular cases.
It's a semi-direct product with a representation of the homotopy.
Okay, yeah, right.
It's a semi-direct product with a representation of the homotopy.
So that's if one just stick to standard notional representation, then things are more complicated than compared to the groups and the algebra. But this representation of homotopy basically fix the problem at the price, of course, of introducing new objects. Yeah. Okay, and here I wanted to say that what is here the core? Well, that's very simple to see because it will be, according to the previous definition, the kernel of the S intersected with the kernel of this. So it means they are just the tangent vector, which are tangent to the fiber, and they are based at the unit points. Well, this means this is just the Lie algebroid canonically associated to a Lie groupoid. For those that don't know it, in the same way that any Lie group induces a Lie algebra, any Lie groupoid induces a Lie algebroid, which is defined precisely in this way. And what was before the core anchor is precisely just the standard anchor that any Lie algebroid has. This is the tangent VB-groupoid, and there is another nice example is given by the cotangent Lie algebroid, the cotangent VB-groupoid, which is defined in a similar way, but not exactly the same. Because here I take the cotangent bundle T star G over G, but here I cannot take T star M. So it was actually studied that, I mean, in order to get a nice a natural VB-groupoid structure, here I have to take the dual of the algebroid. With that one, I get here a Lie groupoid structure, which is just slightly more complicated to write. There is something which involves the right and left translations. And if I look what is the core here, the core will be the dual of T star M. So this kind of example, you see some kind of duality where the role played by the base and the core is swapped. This is not a coincidence. Yeah.
Not exactly the same, because tangent is a functor, while cotangent is not a functor. For instance, if G is a Lie group, then TG is also a Lie group. But if G is a Lie group, then T star G is not a Lie group. This is exactly a groupoid. Yeah, so this is a big difference.
Yeah, that's why, I mean, what I meant is that one could try to apply the same principle, so T star G is a vector bundle, that at least is true, but if one also wants to incorporate the groupoid structure, one cannot take T star M, but as you mentioned, one has to change a bit the construction. This is not a coincidence. As I said, there is really an entire theory of duality for VB-groupoid. So if I start with any VB-groupoid with any abstract core C, then one can define what is the dual VB-groupoid, which will be a groupoid over the dual of the core, and which have core the dual of the base. So there is really, that's why also here with this nice notation with LK, this become the rank become KL. So all this duality thing has been treated, what you can read in the book by Mackenzie or other sources. Another nice particular kind of VB-groupoid I want to mention are those which are sometimes called trivial core or trivial base. Trivial can be a bit misleading. Actually, I don't mean here trivial as in trivial vector bundle, but I mean just that the core here will have rank 0. And in that particular cases, one does not need to go to representation up to homotopy, but one can just see that the base here, EM, will have a natural representation of C, such that the top manifold here, EG, must be isomorphic to a groupoid of this kind. It will be the action groupoid associated to that representation. So in somehow, if I impose this condition, then I have a very restrictive choice of what could be on the right-hand side. So E must be of this kind. And if I go in even more particular cases, and I started with the previous case of the tangent groupoid, if I start with TG and then I impose that the core is 0, this means that the algebroid is 0. But a Lie groupoid with algebroid 0 is what is known as an étal groupoid. So it's something where dimension of G and dimension of M are the same. So it could be not very interesting or interesting depending on what you're doing. And so in this case, one recovers precisely the canonical representation that every étal Lie groupoid has on Tm. So this is like one extreme cases. And another one, of course, is the same when one considering instead the base to be trivial, or better the base to be rank 0. Also in that case, then the core is endowed with a natural representation of G, and then the manifold here must take absolutely this form. And in the particular case, when here I have Tg and Tm, well, if I have the Tm as rank 0, this means that M, my manifold, has dimension 0. So I don't have much choice. It means that here is 0. My Lie groupoid is a Lie group. My core must be the Lie algebra, and the representation that I take here is precisely the adjoint representation that I have of a Lie group on its Lie algebra. Okay, so this was a bit of an introduction on VB-groupoid. Now let's look at the frame. So the idea is that we can consider standard frames of a vector bundle, in particular this vector bundle EG over G, but then we want to encode ask a compatibility condition with also the groupoid structure that we have. So we have the following definition. We take we fix a frame, phi G, so it will be this linear isomorphism, and then we call it adapted to our VB-groupoid structure if it first satisfies two extra compatibilities. Now here I put it just schematically, I don't want to go into technical detail. The first compatibility is the following triangle. So it means that we want to restrict the frame to the second group of coordinates. So we put 0, the coordinate in RL, and we consider only the one in RK. We go to EG, and then we go down using the source to EM. The condition is that this map here, that we define this triangle, must be a linear isomorphism. So somehow, if a frame is adapted, then we get a natural frame of EM. That's one condition. The second is something similar using the core. So in this case, we restrict the frame to the first group of coordinates. We put to 0 the second one. And then we apply, well, not S, but the multiplication by 0, which is something which ideally play the same role as the right multiplication, if this was TG, but in this case it's something more general than TG. And they want it to land in the core and this to be an isomorphism. So there are two certain conditions, but the moral of the story is just that one involved restricting the frame to the first group of coordinates, the other restricting the frame to the second one. And of course, it seems that there is an asymmetry because I choose specifically here S and here the multiplication on this side. I could try to choose, of course, I would have other alternative options, but these I don't need to care of them because they are automatically true. So it follows that if I have a frame which is adapted in this sense, then also the same diagram that I have here with T star, using T instead of S, will also be a linear isomorphism. So I also get, in total I get two frames of EM, one here and one here. I have here a frame of C, and I want here another frame of C, which also happens. It's just that here there is a few extra technicality. So basically one cannot just take the restriction of this frame to the first group of coordinates. One has still to take non-zero coordinates in both of them. And in order to make this work, there is an extra map here that I denoted by D in red. So that is where there are some technicality hidden. But this map basically just built using this row, this core anchor. So the reason that I mentioned it before is just because it comes into play for this part. But you don't have to understand the details for that. The goal here is just to say that we have a frame which is compatible with the groupoid structure. And because of this compatibility, I get two frames of EM and two frames of C. And this I use it now to define a Lie groupoid structure of this set of adapted frame on the base, which is this product of frame of C times frame of E. So somehow I need to consider both sides. It's not enough to just say I have a groupoid structure on the frame of EM, for example. And the source and the target of this groupoid will be precisely given by those four linear isomorphisms which I defined before. So somehow we reverse engineering the definition, starting with what we got in order to make the machine work. Of course, these are only the source and target. In order to give a complete definition of a Lie groupoid, one also take care of the other aspect, but these follow from the rest. So I just put it here just so that you see, you can read it in the paper, and there is also the proof and everything, what would be the multiplication, the unit, and the inverse map. So we have our frame of a VB-groupoid, we restrict it to this adaptive frame, we get for free this Lie groupoid structure. But that's not enough, because we also want to take care of the principal bundle structure. Remember, our goal was to reach some kind of PB-groupoid. So there is another proposition, which says that there is a natural action of a certain object. I will explain the name in a bit, so here is written just strictly to groupoid or something, but is a natural action, but natural in the, not in natural like it's as in easy and normal, and the name here is this object GL, so it's something that should play the same role of the natural action that one have of GLK on the frame bundle. Just that here is a bit more complicated because there are more manifolds involved. And using this action, so I will be more precise in the next, one have a diagram of this kind. So we have G over M. Here we have our VB-groupoid, of which we took the frame, this frame adapted to the VB-groupoid. This will show that it is a Lie groupoid over this product here. Now we want here some object that act in the right way on here. So in particular, there will be some groupoid here, GL2, which is a groupoid over GL0, acting on this top manifold. And then another groupoid, GL1, which acts on this other manifold over GL0. So here again, I should mention for people that are not familiar with Lie groupoids that there is a notion of Lie groupoid action, which is also very similar to a Lie group action. But the main difference is that because in a Lie groupoid there are two manifolds, G and M, if I say that a groupoid acts on something, I have also to provide an additional data, which is a map from the something, which will be, in this case, also from the manifold where it is act to the base. Now, this is, I will explain now in the next slide. So I will have to start first by be precise what I mean by this strictly to groupoid. Because there are actually many people, I think possibly also in this room, that work on Lie to groupoids, but there are different notions. So here I call it, not I call it, other people call it strict, because these are to distinguish with what other people call weak Lie to groupoid, which is something defined involving simplicial manifolds. That's not what we are using here. Here we are using actually a kind of double Lie to groupoid, so it was also mentioned by Janusz, which has this extra property where the base is the unit groupoid. So this means that we have a structure where with four manifolds, all of these are Lie groupoids structures, and all compatibilities, like all these maps, are Lie groupoid maps. But here on the base, I have actually the same manifold. So this one is a stupid groupoid called a unit groupoid, where I can just do nothing with it. So that is what it is, a strict Lie to groupoid. And now, what I was mentioning before is that there is this natural object for given any two number Lk, then I can just define this general linear two groupoid. And what is that? So, well, GL0 is just simply the linear map from RL to RK. Okay, that doesn't tell me much. GL1, you have to interpret it as the object which have an action on this frame of C times frame of E. But we know already that those are actually principal bundle. So on frame of C, there is already a GL with act on it. And on frame of E, there is another GL that act on it. So I just need to put together those GLs in order to make it into a Lie groupoid action. And that's why here there is also this times RL, RK. And similarly for GL2. So in GL2 case, I need to have something that acts on the frame of EG. Well, if it was the whole frame of EG, then I can just take GL of the appropriate dimension. So GL of L plus K. But in this case, I'm considering also an adapted condition. So I need to take something smaller than that. So I need to restrict it suitably. So here, that's why here there is just a subset instead of an equal. I don't want to be more precise about what is actually this particular object. It's something which involved several linear algebra computation. And indeed, we were drowning in the linear algebra to understand precisely what this object should be. Therefore, just so I can support the state that was made before that talking with people is useful, Luca Vitaliano saved us once discussing with us because he pointed out to us that other people already did the dirty work for us. So we actually found out that this object we were looking for is a particular case of an object already defined in other two papers. So there is this object called general linear two-groupoid GLE by Deloy and Stefani, and another object called two-gauge groupoid by Brahic and Ortiz. And those, they actually were interested in looking at representation up to homotopy, so they have their own reason to define those. In our case, we just need to take the result and take a very special case, but that at least does the job for us, so we don't have to care furthermore about understanding the structure here. So now, with this, then we have this definition that what is an abstract PB-groupoid? Well, it will be a diagram of this kind, where I have Lie groupoid here, and then I want to have principal bundle in the right way. And the right way means that I need to start here with a strict Lie groupoid, H2, H1, H0. So I have H2, which is a groupoid over H0, which act on P. Then I have H1, which is also a groupoid over H0, which act on this other P, on PM. And then I need more, because here I also have a structure of groupoid of H2 over H1, which I haven't used yet. And this is because it comes in this other condition. I want the action map to define a Lie groupoid morphism. So if I write down the action map for this action, this is something from a Lie groupoid to another Lie groupoid. So this has to be a Lie groupoid action, a Lie groupoid morphism, and it involves this extra condition. This would be an action of a strict Lie groupoid on a Lie groupoid, and then I have to impose principality. But that's easy because that's the standard notion. So I can ask the action to be free and proper, or simply saying that the quotient of this action must be isomorphic to this groupoid that I have here on the right. Yes.
Bundle and Lie groups. What is this diagram?
Very good. So that's here. So as particular cases, there has been actually several people that started to that look at some cases of this object. So in particular, if I take H0 equals 0, then it means that here I have nothing, and here I have two Lie groupoid over a point, which means just a Lie group. So I have a Lie group here and a Lie group here, such that this is a Lie groupoid. So this is what is known as a Lie2 group, or a strict Lie2 group, actually. And in that case, so one just have a strict Lie2 group acting on this manifold, which is also here a Lie groupoid. And those have been known as principal two bundles.
Could you comment on structural groups in this case?
Well, structural.
So you have principal bundles. So yes. What are structural groups of this bundle?
In this case,
in general case.
Well, it depends. So this principal bundle has a structural Lie groupoid, not a structural group, precisely because it's not a principal group bundle. It is a principal groupoid bundle. In the particular case, which is indeed what Barbara was asking, I have as a structural group H2, which should be a group, because this is 0, and as a structural group of this other bundle, H1, which is also a group itself. And this is what indeed people have called principal two bundles or principal bundle.
These groupoids or groups should be related somehow, yeah?
Yeah, it should be related because there is still errors here. So it is, you can see this also as a group object in the, a groupoid object in the category of groups, for example. So it is really, it is the definition of a Lie2 group, or strict Lie2 group. And one can go even more specific, and that's, for example, also was related to one of your work and other people, where they consider also here the case of Lie2 group, where H2 and H1 are actually the same. So one have one single structural group which act both on the top and on the bottom. So all of these will be then particular cases of the definition that we had before. Now let's say start at a quarter.
You start at 12.
You
end at 12.
I end at 12. Okay, thanks. So I can give a couple of extra examples that would be related to basically computing what would be the adapted frames of the example of the VB-groupoids I gave before. So for example, there was here this thing with the trivial core, where the core here was 0. Well, that's very simple, because if we look at the condition of adapted frame, this was something that involves both the base and the core. But here, if I take the frame of the core, well, I have a vector bundle of rank 0, the frame are nothing, because linear isomorphism with a vector space of rank 0. So it means that I completely cancel one part of the structure, and the other structure, then, the condition that I have of being adapted is automatic. So what I'm saying is that if I take the frame of EG, where EG is this object here, then the condition of adapted is always satisfied, and I get the entire bundle frame of E, which is a principal bundle over G, with the standard Lie group GLK. And here on the bottom I have frame of E, which is also the entire manifold, the entire frame bundle, with the standard action of GLK. And so that's precisely an example where this is 0, and this is just one Lie group, and then the same Lie group with a trivial Lie groupoid structure between them. And in this particular example, if one imposes furthermore that EG at the beginning was TG, so the tangent groupoid, then one can even be more explicit and write exactly what the multiplication should be. That would be much simpler than the long form that I wrote before. So that's one case when we don't have to bother about this adapted frame, and the other opposite case also works in the same way. Because now if I consider C, which is a vector bundle, but the base, which is just a vector bundle of rank 0, again, in the adapted condition, I get something which is trivially satisfied and another one which would be automatic. So also in this case, if I look at the adapted frame, then I would get here the same manifold frame of E. And in this case, well, before all the orange part were going away, now all the blue part goes away. So I get GLL, where L was the rank of this bundle here, since this bundle here is rank 0, so there is nothing to do with that. And again, I get this kind of same object. So here, these nice Lie groups acting here. And also in this case, if I consider the tangent bundle, then I would just get an easy expression of the multiplication. Something else that also we worked out in the paper to understand better this notion was this notion of duality. So we had before that the duality that for any VB-groupoid, one can always define a dual VB-groupoid, where the role played by the core and by the core and the base, they are just swapped. So in this case, one can just start with this VB-groupoid and its dual, and we can consider this adapted frame for both the groupoid and the dual. And what one could guess is that these two actually turn out to be isomorphic. So this actually, it is true, even if it's not immediately obvious. There is actually a couple of lemmas that need to be proved to check this. But one have this, which is a VB-groupoid over this product, frame of C, frame of EM, and another over the product, frame of E star times frame of C star. So of course, the vector bundle below, they are all isomorphic because they are just one dual of the other, but above, there is this adapted condition behave well corresponding with respect to duality. And then also we looked, of course, at some other particular cases like the pair groupoid, so something which is very simple where one can compute precisely what is this condition. But so altogether now, it means that if we look back at the correspondence we had at the beginning, we wanted to start now not with vector bundle, but with VB-groupoid of a certain rank. And we have constructed what should be now the frame bundle of this vector bundle, which is this object that we have defined above, which is a PB-groupoid, which have a structural Lie2-groupoid GL. On the other hand, one can also go to the reverse arrow. So before the arrows was defined as the construction of the associated bundle. So also here, I could start with an abstract PB-groupoid, not necessarily of the form or the frame, where I give it actually an abstract structural Lie2-groupoid here. Of course, for this to make sense, I need to impose an extra data, which in the previous case, it was just a representation of a vector space. Here, it will be something more like a suitable notion of two representation. But using that one, then I can just mimic the same construction. So I didn't give detail about that, but that's because this is really similar, analogous to the standard case. I can just get here some associated bundle and get precisely a VB-groupoid which has rank equal to the rank of those bundles. But in conclusion, I get what I want at the beginning, which is a correspondence between VB-groupoid of a certain rank LK and PB-groupoid, which have as a structural Lie-groupoid this object is GLK, which plays indeed the same role as the general linear group in the standard theory of principal bundles. So this was our main objective. That, of course, is only the starting point for many further works. So I will just conclude now, but with a few open questions and problems that we want to look at. So one, for example, is going to the infinitesimal point of view. That's a classical thing that one always tries to do when looking with Lie-groupoids, because Lie-groupoids are difficult objects in general. Lie algebroids are usually easier to treat, simply because they are linear objects, and usually linear algebra is complicated, but not as complicated as other parts in mathematics. And I mean, that's the same principle that one works with Lie groups with infinitesimal point of view, which are Lie algebras. So here one could have, there is a notion of VB algebroid, which you can guess what it is. And also in that case, we would like actually to understand some kind of adapted condition on the frame of a VB algebroid, and look at if this object we would like to be the infinitesimal counterpart of PB-groupoid. So that then one could just transform global problem into infinitesimal problem. That would be one kind of problem. Another one involves the notion of connection, because there could be here a nice interplay. One have notion of connection for Lie-groupoid, but also for principal bundles, and this would be nice to see some kind of interplay of this notion of connection, precisely because connection where one of the objects that in this correspondence were used were corresponded from the linear and the principal side. So also in this case, there could be some interesting stuff to say about connection for PB and VB-groupoids. Another thing which I'm interested in looking in this is the notion of G structures on Lie groupoids, because as I mentioned, G structures can be defined as a reduction of the structure group of the frame bundle. But if I look at a Lie groupoid, I can consider just the frame bundle of its tangent groupoid of TG, and then I could try to look at reduction of these objects. So this should actually be able to, I should be able to use this in order to define a geometric structure on a Lie groupoid. The tautological form would be is one of the main tools that people use in the theory of G structures to make sense, to prove some properties and to look, for example, at the integrability conditions. And so in this case, one has also to make sense, what does it mean to have a form, one form compatible with all these groupoid structure? And related to that, one can go a further step and look at Morita equivalence between these kind of objects. So Morita equivalence is an important notion between two Lie groupoids that says that when two Lie groupoids behave in a very similar way somehow, and this also is the starting point to define what is called a differentiable stack, which can be seen in a much more categorical and abstract way, but in practice could be seen also as a Morita equivalence class of a Lie groupoid. And in particular, these stacks can be used to formalize many kind of manifolds which are not really smooth, so they admit some singularities. So it is natural to see that there will be some geometric structure defined on manifold with certain singularities, modeled via differentiable stack, and hopefully this point of view would be able to see if this kind of geometric structure on Lie groupoids would go down to a differentiable stack, being compatible with the Morita equivalence. But these are all stuff that hopefully I may say next time. Thank you for the attention.